So a buffer solution, it's a solution of weak acid or base and its conjugate base or acid. So you have two species that are conjugate to each other. And a buffer solution has a very interesting ability to resist changes in pH upon addition of acid or base via the common ion effect. So again, usually if you add like a strong acid or a strong base to a solution, you get a lot of H3 plus, a lot of H3O plus, or a lot of OH minus. But if you can absorb both the OH minus and the H3 plus, then it won't change very much in pH. So the more concentrated the weak acid or conjugate base, the better the buffer. So simplest buffer would be just equal amounts of an acid and its conjugate base. Or one could create that by, say, taking a certain amount of weak acid and then add exactly half that amount of a strong base, which would create equal amounts of acid in the conjugate base. So 0.05 molar sodium acetate and 0.05 molar acetic acid would be a good buffer. Let's say we had 0.1 moles, and here I'll go with moles so we don't have to worry about changing the volume of the solution as we go. 0.5 moles of sodium acetate and added 0.05 moles of hydrochloric acid, that would create a buffer of sodium acetate and acetic acid. By adding the hydrochloric acid to the sodium acetate solution, I'm creating acetic acid. Okay. So as I've said, a buffer solution, a solution that contains a weak acid, its conjugate base, resists drastic changes in pH. So if we have a weak acid and conjugate base, some examples would be acetic acid and acetate, hydrogen fluoride, hydrofluoric acid, and the fluorine ion, ammonium and ammonia. And this last one is interesting, H2PO4 minus, which would be phosphoric acid minus one of its hydrogens, plus HPO4 2 minus, which is phosphoric acid missing two of its hydrogens. And in this case, you can create a buffer there because those are conjugate acid and conjugate base pairs. Okay, so thinking about the chemistry of why this happens. So let's say we have an original buffer solution that has equal amounts of weak acid and conjugate base. When OH minus is added to the solution, some of the weak acid is neutralized and thus converted into conjugate base. The OH minus doesn't go free in solution, instead reacts, creating a little more conjugate base, but you're keeping the ratio of weak acid to conjugate base pretty close. On the other hand, if you add H3O plus, some of the conjugate base is neutralized and converted into the weak acid. And so the H3O plus, instead of going into solution, goes and reacts with the conjugate base to produce more acid. Your ratio of base to acid changes, but most of the vast majority of the H3O plus doesn't go directly into solution. So as long as the concentration ratio of weak acid to conjugate base stays close to the original ratio, you won't have much of a change in the hydronium and the hydroxide ion concentrations. Because all the added hydronium and hydroxide reacts with either the acid or base and thus are not available in solution to react with something else.